Hi there. I wanted to make a video explaining the proof of the chain rule because I haven't really been able to find a video that easily explains in sort of layman terms what's going on in this particular proof of the chain rule. This proof that I'm about to go over is from Calculus Early Transcendentals, 8th edition by James Stewart, and it's a pretty straightforward proof after you get the preliminary work out of the way. So with that said, let's get started. So if we have a function y equals f of x, and x changes from a to some point later on in the x-axis, we'll call it a plus delta x, we can define the corresponding change in y as delta y equals f of a plus delta x minus f of a. So let's talk about the derivative for a little bit. The definition of the derivative is the limit as delta x approaches 0 of delta y over delta x. So that's the definition, but we can also write the derivative in shorthand as f prime of a. So I want to emphasize that these two things are the same. If we plug numbers into both of these, it's just like saying we have 2 equals 2, or 4 equals 4, 10 equals 10. What do you think would happen if we subtracted f prime of a from both sides? Well, we would get 0, because since they're the same thing, if you subtract 2 minus 2 is 0, 4 minus 4 is 0, 10 minus 10 is 0. They might look different, but they are indeed the same. Let me ask you a question. What do you think would happen if we just didn't let delta x approach 0? What would we end up with? That idea of not letting delta x approach 0 is one of the focal points of this proof. It's similar to an analogy. For example, if we had one of those wind-up toy cars that you can wind it up by rolling its wheels back on the floor, and then once it's wound up, if you let it go, it starts driving by itself. You can think of delta x as the car. So we're winding up the car, we're getting delta x ready, but we're not letting it yet approach 0 because we're trying to get this into something usable. So if we don't let delta x approach 0, what we're left with is just plain old delta y over delta x minus f prime of a. What is this equal to? Because we no longer have the derivative minus the derivative. We no longer have 2 minus 2 or 4 minus 4. Because delta y over delta x is not the derivative, it's just the difference quotient. The answer is that we don't know what this is, but we also don't care what this is. However, since we don't know what it is, we need to represent it by a variable, and we're going to choose that variable to be epsilon. And that's really all that this is saying. So we have epsilon equals delta y over delta x minus f prime of a. And we can just rearrange this using algebra to get it into a usable form, the one that we have up here. So delta y equals f prime of a times delta x plus epsilon times delta x. Let's talk about what is going to happen to epsilon when we let delta x approach 0. That is, what's going to happen when we finally do let the little car start driving. So if we let delta x approach 0, we actually already talked about that earlier. So if we take the limit of both sides, we get the limit as delta x approaches 0 of epsilon is equal to the limit as delta x approaches 0 of delta y over delta x minus f prime of a, which turns out to just be f prime of a minus f prime of a, because the limit as delta x approaches 0 of delta y over delta x is just the derivative. And because of this result, we can say that epsilon is going to be a continuous function of delta x. Well, why is that? So when you think about what a function is, right, let's take y equals f of x. You put something in and you get something out if it's 1-to-1. If epsilon is a function of delta x, right, if you plug in a value for delta x, you're going to get a corresponding epsilon. Well, we did plug in a delta x. We plugged in as delta x approaches 0, right? We didn't exactly say that specifically delta x is 0, but as delta x approaches 0, you get a kind of idea of where delta x is going. And as delta x approaches 0, you get the resulting epsilon equal to 0, which is what we set up here. That being said, epsilon is a continuous function of delta x. Well, why is it continuous? Because we took the limit as delta x approaches 0 of epsilon, we took the derivative. And if you take the derivative of something at a point, that means it's differentiable at a point. And by definition, if a function is differentiable at a point, it is continuous at a point. So we can say that epsilon is a continuous function of delta x. We can write it delta y in this form down here, and we can define epsilon to approach 0 as delta x approaches 0. And this property of differentiable functions is what enables us to prove the chain rule. So now we can actually get to the proof of the chain rule, since we did all that preliminary work. So we're going to define u equal g of x to be a function, and we're going to say it's differentiable at a, and y equals f of u to be differentiable at b equals g of a. And so we can write the corresponding increments in delta u and delta y as the form that we found earlier. So we can write delta u equal to g prime of a delta x plus epsilon 1 delta x. The reason for the subscript is because we are doing this for two functions, which we defined earlier. So we're doing it for u equals g of x and y equals f of u. All we did in equation 8 here is that we just factored out a delta x. And so we can use a similar process on delta y to equal f prime of b times delta u plus epsilon 2 times delta u, factor out the delta u. And of course, you have to define both of these, that both epsilons tend towards 0 as delta x tends towards 0. So now that we have an expression for delta u, we can plug that into delta y. And we get the result, delta y equals f prime of b plus epsilon 2 times g prime of a plus epsilon 1 times delta x. We can then divide by delta x on both sides. And I want to emphasize here that we are not dividing by 0, because remember, we're not taking the limit yet. We have not let the car go yet. We talked about theoretically what would happen if we let the car go, but it's still in our hand. It hasn't driven yet. So we're not dividing by 0 here. We're dividing by some value of delta x. It could be 0.00001, but it's not 0. But now that we have this in terms of what looks like the difference quotient, we can take the limit as delta x approaches 0. And remember earlier we said, since epsilon is a continuous function of delta x, that it tends towards 0, because if you plug in the limit as delta x approaches 0, the resulting epsilon is 0 as well. So these two terms, epsilon 2 and epsilon 1, are going to go to 0. And what you're left with is f prime of b times g prime of a. And what is f prime of b? Well, we defined b to be g of a. And there you have it. That is the chain rule.